Today's activity is going to be based on the law of conservation of momentum that we introduced on Thursday of last week. That law says that momentum can't be created, can't be destroyed. It can be transferred from one thing to another. In other words, in an isolated system, the total momentum will always remain the same. You guys remember what an isolated system was? No forces in or out, right? Okay. No external forces. No matter or energy in or out. In other words, no external forces acting here. So in an isolated system, this momentum thing should stay the same in any interaction. Here's our problem. Here's our problem. We're going to take two cars, we're going to collide them. We're going to crash them into each other. We want to know if the law of conservation of momentum is valid for that particular collision between those two dynamics cars. One's going to be moving before the collision, one's going to be at rest before the collision. They're both going to be moving after the collision. It's kind of like sitting at a stop sign getting hit from behind by a car, except we're using dynamics cars instead of real cars. Now in this lab, you're going to have three sets of variables, as you will in any activity: the manipulated, the responding, and the control variables. I'm going to help you out with two of these three variables, just because of the way that we're performing this lab. Now, remember, the manipulated variable is the variable that always stays the same. The variable that you change. The variable that you change. The responding variable is what changes because of what you changed. And the control variables, okay, multiple, are what stay the same, the ones that don't change throughout the entire experiment. One variable will change in this activity. Here's how we're essentially going to perform it. I'll give you more details on the procedure in just a moment, but here's how we're essentially going to perform it, and I want you to tell me what the manipulated variable is. We're going to perform multiple trials of sending a car down at various speeds, therefore various momenta, before the collision takes place. So in other words, we're going to push the car down with a certain momentum, let's say 5. It's going to collide with the other car. Then we're going to push it down with another momentum, let's say 7. Then it's going to collide with another car. Then we're going to push it down with another momentum, let's say 12. Then it's going to collide with the second car. What's the manipulated variable there? What momentum? Okay, so that would be the initial momentum, right? So the manipulated variable here will be the momentum that you start with, because that's what you're changing. Now, somebody might say it's the initial velocity, isn't it? Because we're changing the velocity of the car. Yes, you're changing the velocity of the car, but only so that you can change the momentum of the car. So strictly speaking, the manipulated variable will be the initial momentum of the car, because that's what we're trying to study. What do you think the responding variable is going to be? Without me saying anything else, what do you think the responding variable will be? Yep, Ken? Final momentum, right? We're going to see what the final momentum is in response to whatever the initial momentum is. Now, hopefully, it's the same, right? Because that's what we're trying to do, is verify that momentum stays the same. Control variables are everything that stays the same. Now, you guys are going to have to come up with some control variables yourself. Hey, I don't want the ones that said, like, the amount of sunlight on the car. Like, really everything should stay the same, right? But those ones aren't really that important, right? We want the important ones, and there's usually one or two fairly important ones that we don't want to miss, okay? This is what your apparatus is essentially going to look like. There's one small change here because one of these pictures is an older picture, but it's essentially going to look like this. You're going to use a dynamics track, okay? That's this thing right here. A dynamics track. Okay, on that dynamics track will be two dynamics carts. We'll call this cart number 1. We'll call this one cart number 2. Although if you reverse them, it wouldn't be the end of the world, as long as you're consistent throughout your experiment. Okay, cart 1, cart 2. Cart 1 will be sent down towards a stationary cart 2. They will stick together and go off as one object. How are we going to make them stick together? Daniel? We're going to use sticky tack or fun tack, right? My suggestion would be put the sticky tack on both of them. Put the sticky tack right here. Put the sticky tack right here. If you put it on one of them, they tend not to stick together all that well. If you put it on both of them, they do stick together pretty well, and you shouldn't have any trouble even the first time you try it. Now, before you actually send one cart down and collide with the other cart, we're going to need the mass of both of these carts. Okay, the mass of cart 1, the mass of cart 2. They'll be different. I want you to use the triple beam balance scale to do that. Most of you should have used a triple beam balance scale before, either in Physics 20 or in Chemistry or in Science 10, whatever. If you're not familiar with how to use that, just let me know and I'll help you out with that. Now, here's the big thing. How are we going to measure the velocities? Okay, the mass is easy. We use a triple beam balance scale. But to get momentum, we need velocities. To get velocities, we're going to use what's called a motion sensor. That motion sensor is going to detect several times per second the position of the car, of the first car, this one right here. Now, after it collides with the second car, then it's also detecting the position of the second car because they'll both be in the same place, right? They're stuck together. And what it's going to do essentially is plot a graph for you, a position time graph. From that position time graph, we're going to be able to determine velocities. You guys know how to do that, right? We'll talk more about that again in just a moment. Basically, though, it's going to measure the position and the time of the cars both before and after the collision. That's what's going to give us velocity. But how are we going to read that position and time of the cars before and after the collision? Well, that motion sensor is attached to this little thing that we're going to call an air link. This is actually an older version that you see right there. The newer version is smaller and is a little bit more streamlined here. That air link will actually be connected via Bluetooth wirelessly to your iPhone. The graphs will automatically come up on your iPhone, so you'll see instantly, real time, what the graph should look like here. Now, eventually what you're going to do, you're not actually going to use the graph from your iPhone. It's just going to be kind of a guide. Hey, did it work? If I can see the graph, it worked. Okay? What you're going to do eventually is actually email a spreadsheet file to yourself and to your partners so that you can do the analysis that way. Yep. Yep. Now, what are you going to do here? Once you've done a trial, repeat the trial. Repeat it. Repeat it 8 or 10 times so that ultimately we get 8 or 10 initial momentums and 8 or 10 final momentums. One little thing, when you look at that motion sensor, here's a blown up version of the motion sensor. There's a little switch on it. There's a little switch that you can flip to a guy walking or you can flip to a little cart. I want you to flip it to the little cart. Okay? When you flip it on this setting right there, that allows us to measure the position of something that's fairly close to us, something that's fairly small and close by to us. If we put it on the other setting, the guy walking, that would measure the position of somebody across the room, a big object that's far away across the room. Okay? We want to measure a close by object, a close by small object, i.e. a cart. Okay? Now, how you use that app, how you use that, how you end up hooking it up and so on is on an instruction sheet that you're going to get in just a few moments. So don't panic about that stuff here right now, okay? As long as you understand the basic setup of this, then the instruction sheet will explain the rest of it in terms of the intricacies of how you're actually going to record data. Now, you should get graphs for each trial that looks something like this. Okay, again, this is what it's going to more or less look like on your iPhone. You will not actually use that graph that's on your iPhone. Okay, you're going to use the numerical data that's on your iPhone. But again, this will tell you if you've got a trial that looks something like the way that it should. This data right here, this is position time data for one trial. This data right here seems to be a flat line. What do you think that corresponds to? What's happening right there in that first section of that graph? Yeah. It's not moving. So in other words, we started collecting data before we sent the cart down to strike the second cart, right? That's good. We want to do that. Okay? But what I want you to do, though, be careful with that, just ignore that data. Start collecting the data before the cart moves, just so that you make sure you get enough data. Okay, but delete the data, delete this data here from before the cart moves. Now there's two more distinct sections here. There's this one, and then there's this one. Seem to be fairly close to two straight lines, but with two different slopes. What do you think the first one represents? Yeah, right? The initial velocity, right? Not initial momentum. You have to multiply that by mass to get initial momentum, but it's going to be initial velocity of car number one, right? Because car number one is the only one that's moving. What do you think the green one's going to represent? Maria just told me the blue one is the initial velocity. The green one is the final velocity. It's a smaller slope. Why do you think it's a smaller slope? Going slower, right? But why is it going slower? Why is car number one going slower after the collision takes place? Because it's sticking to car number two. So now it's got not necessarily twice the mass, but it's got more mass than it had before. Same momentum, theoretically. Okay, at least that's what we're predicting. Same momentum, more mass has got to have less velocity. You're going to see 10 of these. Now, it gets a little bit tricky here for the analysis. We'll give you lots of time to complete the analysis here, but it gets a little bit tricky. What you're going to do, again, is email the data to yourself. Then, what you're going to do for each trial is delete some of the data. Delete the red data. We don't want that. Okay, that's before the car started moving. Then you're going to have to, on a spreadsheet, and I'll show you how to do this later on after we actually do the activity, make this into two graphs. Position versus time, position versus time, the initial, oops, I don't want red there, I wanted blue. The initial and the final data. You will get a velocity for trial one of whatever. You will get a final velocity for trial one of whatever. Then you're going to do that for trial two. Then you're going to do that for trial three, and trial four, and trial five. Looks like a lot of work. Okay? It is a fair bit of work, but believe me, it goes a lot quicker than you might think. Okay? You got to have to plot a lot of graphs, but I'm going to show you how to do it on a spreadsheet so that it goes very, very quickly for you. So that's one trial. Okay? Multiply that by 10, and you've got, what, 20 graphs there. Then you're going to record all your data. Mass 1 and mass 2 you've already recorded. The initial velocity of cart 1, I guess it was in blue. The final velocity of both cars for trial 1. The initial velocity for trial 2, the final velocity for trial 2. And so on. So on and so on and so on. The big part of this is now done. The big part of this is now done. There's one thing left that you have to do that right now is going to seem a little bit tricky to you. But believe me, when you go to actually do it, it's not going to be hard. It's going to be the easy part. We've collected data. Now it's time for the analysis. The analysis is going to consist of one graph. So if you have 10 trials, you're going to end up with, in this activity, 21 graphs. I know that sounds like a lot, but it's not nearly as bad as it seems, I promise you. The first 20 graphs are going to be position versus time for initial and final for each trial to get your initial and final velocities. Once you have all of your initial and final velocities in your data table, then you're going to plot a graph of final minus initial velocity. And that graph should look like this. Should be a straight line. Now, what are you going to do with that graph? You've never seen this graph before. VF versus VI. Never seen that before. You will see a question on your diploma exam, I promise you, that is a graphing question. It may involve a graph that you've seen before, or it may involve a graph that you see for the very first time at the end of January as you're writing that exam. We have to know how to deal with it if it's a graph we've never seen before. Here's how you'll deal with that if it's a graph you've never seen before. And we'll do this lots of times through the semester, but this is the first time. You've got a straight line graph. Every straight line graph is represented by this equation, y equals mx plus b. That's from math class, right? Math 9. Years ago, I taught Math 9. I know that you learned this in Math 9, y equals mx plus b. Y is my y-axis. My y-axis is VF. M is the slope. I'm going to write out the word slope here. Okay, I don't want to use the variable or the symbol m because I don't want to get that mixed up with mass. My x-axis is VI. I've called it V1I there because it's the first car that's moving, but in the end, if we want to call it VI, that's okay, since there is only one initial velocity. What's B stand for? I know you learned this in grade 9. I know you've done it since grade 9. What does B stand for? B is the y-intercept, where it cuts through the y-axis. You guys remember that? Yeah. Where it cuts through the y-axis. It doesn't cut through the y-axis in this case. It should go through the origin or pretty darn close to it. So let's just cross that off. Now, that's the equation that represents our graph. We need an equation from theory that is applicable here. Well, we're talking about colliding two cars. The equation that's applicable here is Pi equals Pf. The initial momentum equals the final momentum. We're going to say m1 v1I plus 0, right? In momentum of car 1 plus the momentum of car 2 equals mvf. This m being the total mass here. Let's rearrange this. Why did I rearrange it to solve for VF? Because that's what I have over on the other side. The equation that comes from the graph, solve for VF. The equation that comes from my theory should also solve for VF. Now, watch this. This is kind of a neat little trick that comes up here. Cross off VF because it appears in both of them. Cross off VI because it appears in both of them. What's left? The slope, m1 over m. That means the slope of this graph is m1 over m. Last year in Physics 20, you guys learned the slope of a position time graph was velocity. How do you know that? Because your teacher told you that. Not because you learned why. You didn't learn why it was the velocity or why the slope of a velocity versus time graph was acceleration. Your teacher told you, you believed us. Okay, that was it. Now you know how to find the slope. Okay, what the slope represents. In this case, it represents mass 1 over the total mass. M would be the total mass, right? Both cars combined. Almost done. Almost ready to actually begin collecting data. You will get the slope from your graph. In fact, a spreadsheet can do that for you. You don't actually need to calculate it yourself. A spreadsheet, and I'll show you how to do that. The spreadsheet will do that for you. You can calculate this value, m over m, m1 over the total mass, because you've got the masses, right? So calculate this. Calculate this. If they are the same, then momentum must have been conserved. Think about that. Why does momentum need to be conserved if those two numbers are the same? Well, because we made an assumption here. We assumed Pi equals Pf. If the numbers we get are equal, then that assumption must have been correct. Does that make sense? If our assumption was wrong, If PI equals PF wasn't true, then we wouldn't have got two numbers that were the same. Thank you. So if those two numbers are the same, then momentum is conserved because we made an assumption. We made an assumption that it was true. Since the two numbers worked out to be the same, the assumption must be correct. Within 10%. Let's say within 10%. They're not going to be exactly the same, right? But if they're 4% off, then all right, let's say it's good. If they're 8% off, let's say it's good. If it's 15% off, let's say, nope, wasn't conserved. Momentum was not conserved. That's okay, by the way. If your conclusion is that momentum was not conserved because it was 15% off, that's okay. You can get 100%, okay, as long as your data agrees with that. Your conclusion is, did you verify it? How do you know? And then, of course, after you do your conclusion, you need one more thing, which is your sources of error and ways to improve those sources of error. What could have went wrong? What wasn't great with the materials? What wasn't great with the procedure? What wasn't great with your time management? What wasn't great with whatever? Don't say a source of error was your partner. Let's not go there. I get that all the time, though. Please don't say that. Let's look at inanimate things, okay, or choices you made.